Thank you, Regina. Good afternoon, everyone. First, thanks to DDL committee for giving me this opportunity to present our study on environmental sustainability of inhalers. This is a study which I conducted with Professor Azab Ajek at University of Manchester and was published last year in Journal of Clean Air Production. So, firstly, I will give you some background on the importance of the sustainability of inhalers to set the context of this study. Then we'll talk about the life cycle assessment, which we used as a methodology to assess the environmental impacts. This will be followed by the discussion on the results on carbon footprints and various other environmental impacts. In this study, besides assessing the current situation, we looked at various potential options which are currently being considered to reduce the carbon footprint of impacts. And here we also looked at what will be the implications on the other environmental impacts if we switch to low carbon alternatives. pMDIs have been used since 65 years for the treatment of respiratory related ailments, and they have played a vital role in the delivery of drugs for asthma and COPD, and they still continue to be method of choice for the treatment of these diseases. Originally, they were manufactured using chlorofluorocarbon as a propellant, which provided a driving force to atomize the droplets of drugs for the deposition in lungs. However, these chlorofluorocarbons had a high ozone depletion potential, and in late 80s as well in 1990s, when the Montreal Protocol came into force, these inhalers were switched to low ozone depleting substances, which are known as HFCs or hydrofluorocarbon, or sometimes also called as hydrofluoroalkanes. Currently, the two most common used propellants are HFC-134a and HFC-227ea. However, these propellants still have high global warming potential. HFC-134a has equivalent to 1,300 kilogram CO2 equivalent per kilogram, while HFC-227ea has even 3 times higher. Currently, more than 630 million pMDIs are manufactured every year, which use around 10,000 tons of propellants. In the UK health sector, pharmaceutical contributes to roughly a quarter of their emissions, and pMDIs are the single largest contributor for the pharmaceutical related greenhouse gas emissions. That's why in NHS commitment for net zero, they feature, and there are targets being set for the low carbon alternatives. Currently in the UK, more than 70 million inhalers are prescribed per year. Here I'm talking about pMDIs and DPIs. There are also other forms of inhalers such as nebulizers, which we didn't consider in this study. 3/4 of them are 134a based inhalers, and 22% are DPI. HFCs 227ea based are only small percentage of 2. These inhalers are manufactured in various sizes. Currently the most common prescribed sizes in the UK are for HFC-134a is 200 actuations, and for HFC-227ea are 120 actuations. On the other hand, DPAs, there are various formats available, and 60 inhalations and 120 inhalations are most commonly prescribed. Besides the size, the propellant quantities in pMDIs vary. It depends on various factors, including their design as well as the type of drugs and the size of the inhalers. The low charge inhalers or low volume inhalers contain relatively small quantities such as 60 milligram per dose. Here, when I say dose, means 2 puffs. Though dose can vary depending on the severity of disease and the type of disease, but generally 2 doses per or 2 puffs are recommended per dose for various elements. And the high volume or high charge and also some relatively small size inhalers have high propellant quantity per dose, and it can be up to 200 milligram of propellant. So life cycle assessment is a tool or as an accounting approach, if we call it, to consider the all environmental related aspects from resource use to all emissions to air, water, and soil. There is a standard which is called ISO 14040 and 44, which gives a methodological framework and guidelines on how to conduct the study and reports the findings. The framework consists of 4 stages: goal and scope, inventory analysis, impact assessment, and then the interpretation of the results. In goal and scope, generally after deciding the purpose of the study, the temporal and geographical boundaries are defined. What needs to be included and what is excluded is also defined at the onset. And also the unit or comparative unit for the analysis, which we call it functional unit, is defined. This sets the foundation for the next stage, which is called inventory analysis, which is more involved in terms of time as well as resource use. This requires a lot of data collection, where this system under study is broken into several sub-stages, and the data on energy use, material use, as well as emissions to environment are identified and quantified. Once those inventory data are collected and analyzed, the next stage is then assessing the environmental impacts. I'll talk more about the impacts in the next slide. And then the results are interpreted again if needed, then the further data collections or scope are redefined if needed to draw conclusions. So goal and scope for this study, the main aim of this study was to assess and compare pMDIs and DPIs for various environmental impacts. And the second aim was to evaluate various alternative options which are currently being considered. The unit of analysis, so we consider 2 units. Firstly, we looked at the 100 doses of inhaled medicine, and secondly, then we quantified the environmental impacts for the annual use of inhalers in the UK. System boundary. So what is included or excluded in this? We looked at from cradle-to-grave approach, which starts from the extraction of raw materials, then manufacturing, transport, usage, and then disposal of the inhalers. We collected as much data as we could especially on propellants as well as on devices from manufacturers, and then the secondary data, especially on environmental parameters, were collected from LCA databases. This chart shows presents the system boundary and what was included for pMDIs. So pMDIs broadly we can say there are 3 components: propellants, device itself, and the drug. With the environmental effects of drugs for both pMDI and DPI were not considered in this study, so we focus on those remaining 2 components. The production of the propellants, HFC-134a, which is made from the hydrofluorination of trichloroethylene, while HFC-227ea is made from hydrofluorination of hexafluoropropene. So we collected data for the production of the raw material, energy use as well as any emissions occurring during the production. The HFC gases are used for various industrial purposes, but for use in these devices, they are further purified to medical grade. So this will again require further use of chemicals as well as energy, and the emissions occurred during those processes were also accounted. And the device pMDIs are made from aluminum as well, and they are coated with Teflon, and there are also various plastic parts. So that time those were collected. In the use stage, the most of the emissions related to of the propellant would to the atmosphere would occur. So these were accounted, and finally the waste disposal, which can be either incinerated or landfill or recycled, were considered. For a comparative purpose, we follow the similar system boundary for dry powder inhalers. There are various formats of dry powder DPIs are available. Here we consider blister-based discus inhaler, for which is mainly made of various polymers such as ABS or acrylonitrile, butadiene styrene, and propylene. The blisters are made from films of PVC, aluminum, and polyamide. So all the materials used and the energy used in the molding of the device and the films production were considered. The use stage for DPI is not that relevant from environmental perspective. However, the disposal, which either can be again either landfill or incinerated or recycled, were considered. After collecting the data for both systems, then the next step is to model them and assess the environmental impacts. In LCA, there are various methods and indicators available to assess environmental impacts. Some of them are listed here. The carbon footprint is most commonly used or referred in most of the studies. So this refers to the impact on climate change. It's also referred as a global warming potential impact. This basically accounts for all greenhouse gas emissions in terms of their CO2 equivalent units based on the IPCC Intergovernmental Panel on Climate Change recommended characterization factors. The next indicator, which is here mentioned as fossil depletion, which looks at the resources used, with especially non-renewable fossil resources, and this is more important from the energy security perspective, and the impact is measured in the tons of oil equivalents. Acidification impact assesses the impacts caused due to the acidic emissions such as sulfur dioxide, nitrous oxide, and which then, once released to air from various combustion or other industrial uses, react with the moisture or rainwater, and then can cause damage to plants as well as to various material infrastructures. Eutrophication impact is caused by the nutrient enrichment of which are generally released as part of wastewater from industrial processes or agriculture. These nutrients include nitrates and phosphates. Once they are released in water bodies, they can lead to accelerated growth of algae, which then in turn will reduce the oxygen content and can affect the water life. Human toxicity impacts in LCA account for the impact caused by various pollutants. Some of them can be carcinogenic on health. These are generally measured on the fate and exposure model, and in here we have considered separately cancer-based impacts as well as non-cancer. Ozone depletion impact looks at the impact caused by ozone depleting substances such as chlorofluorocarbons, which can damage the ozone layer in its stratosphere. So after explaining briefly these indicators, let's now look at the results of our study. So this chart presents the carbon footprint results compares the carbon footprints for pMDIs and DPIs. Here the results are shown as for the functional unit of kilogram CO2 equivalent per 100 doses. The results are also, you can see, are shown in ranges where the whisker bars are showing the minimum and maximum range, while the box profile is showing the interquartile range, and the line as well as the labels are the median values. This is this to consider or take into account are the various uncertainty into various parameters. We can see that HFC-227ea has significantly higher impacts than DPI as well as HFC-134a, and estimated at 69 kilogram CO2 equivalent per 100 doses. HFC-134 has 60% lower impact, estimated at 27 kilogram CO2 equivalent per 100 doses, but is still 30 times higher than DPIs. So this chart shows now the contribution of various stages. We can see for pMDIs, the major contribution is due to propellant emissions occurring during the use phase. For HFC-227ea, they account for 90% of the impact, and for HFC-134a is around 98%. For HFC-227ea, the other contribution is noticeable contribution is from the materials used in the production of the propellant. On the other hand, for dry powder inhaler, the raw materials are the major contributors, which are normally used for the production of polymers, and the molding process also account for around 20% of the impact. The other stages such as waste disposal and transports have negligible impact for our inhalers. So we saw that DPI has a significant advantage in terms of carbon footprint impacts over pMDIs. Now let's look at the various other impacts. How do DPI compare with pMDIs? So here again, the impacts are shown as for 100 doses. So for fossil depletion, the DPI impact is significantly higher, around more than 100% higher than pMDIs. Again, this is largely because the polymers are made from oil-based or fossil resources. That's why they have higher impact. There is no significant difference between inhalers for acidification impact. However, for eutrophication, HFC-134 has the lowest impact, while DPI and 227ea has similar impact. Same can be seen for human toxicity cancer. On the other hand, for non-cancer and ozone depletion impact, HFC-227ea has a significantly higher impact. Here I must point out that the carbon footprint impact which we saw in previous slide was in kilogram per CO2 equivalent per 100 doses. Here you can see the impacts are in a smaller units like grams and milligrams. So the order of, though the DPIs have in some cases have significantly higher impact, but the order of magnitude of impacts are much lower. So now let's look at the annual impact of inhalers in the UK. You can see that the carbon footprint, the inhalers contribute to 1.3 million tons of carbon footprint in the UK from the annual usage. This is equivalent to around 4% of NHS emissions. Again, to put into context, this value is around 1.3 million ton is generated by around 600,000 average size cars if they are driven like around 1,200 kilometers per year. For carbon footprint, again, we can see that HFC-134a is the contributes for 96%, and 3% is due to 227ea, and very small percentage comes from DPIs. However, for other impacts, the DPI contribution is noticeable, ranging from 10 to 25% for various impacts, except ozone depletion, where though HFC-227ea, as we saw earlier, only were 2% of the usage, but they contribute to more than 50% of the impact. So there are various options being explored for the reduction of those impacts. One of them is replacement of pMDIs with the DPIs. Second is which is currently already is being used in inhalers, is some of the inhalers are made with low charge propellants. So we looked at if the inhalers can be made, all inhalers can be made if they by 60% lower propellant. One option which is currently being investigated is finding a propellant which has low global warming potential. HFC-152 is one of that, which has an order of magnitude lower than HFC-134a. So we looked at this option as well. Also, it's possible to reduce the recover the propellants from the partly used pMDIs. And finally, we looked at the scenario where all these 2, 3, and 4 options can be combined, where propellant is replaced with 152a, and the charge is also reduced by 60%, and then there is a recovery of the leftover propellant from the used MDIs. So let's quickly look at the results. What are their implications? We can see if these all pMDIs are replaced with DPIs, then in the UK, then carbon footprint and ozone depletion, they are reduced by more than 95%. There is no significant difference on the human toxicity, non-cancer, and acidification impact, but then some of these impacts would increase by 50 to 100%. On the other hand, if the propellant usage is reduced by 60%, then we can see a proportional reduction in all impacts ranging from 40 to 60% for this scenario. If the propellant is switched to HFC-152a, then the reduction in carbon footprint and ozone depletion is more than 90% comparable, which is comparable to DPIs. However, we also see all the other impacts which we considered here also reduced by 20 to 60%. It's estimated that around 10% of on average, 10% of propellant is left in the used pMDIs, which are disposed. If that is recovered and the inhalers are recycled, then they can also reduce the potential impact by 5 to 15%. However, if we combine these 3 options, if HFC-152 propellant is used and the volume of the propellant is reduced by 60%, and then the leftover is recovered, then we see huge benefit in all impacts. So the carbon footprint and ozone depletion, again, they are reduced by more than 95%, but also there is significant reduction from 60 to 80% for all of those impacts. So to summarize, HFC-134a and 227ea has high carbon footprint ranging at 27 and 69 kilogram per 100 doses, which is 30 to 75 times higher than DPIs. For both HFC-based inhalers, the main hardest part is due to the release of propellants at the use stage. Though DPI has a lower carbon footprint, but some of the impacts such as fossil depletion, eutrophications, and human toxicity cancer are higher for them. The annual usage of inhalers in the UK contributes to 4.3% of NHS emissions. Switching to DPI would reduce those greenhouse gas emissions by 96%, but some of the impacts would increase. While switching to low GWP propellants such as HFC-152a the reduction in GWP are similar, but there is also significant reductions in the other impacts. This is the link for our paper, which was published last year. And I also like to thank Mexichem Flor for providing on the data for the product manufacturing process of these propellants. Thank you very much.
Thank you, Harish, for this interesting presentation. I have one quick question for you. And this is related to that it looks like it would be beneficial to move away from DPIs from pMDIs to DPIs, but given that DPIs are not suitable for certain patient groups and maybe also during an acute exacerbation. Should the selection of the device type be driven by environmental impact or by the patient need?
No, of course it depends on the patient needs. That's why we looked at the another propellant. Though in this presentation I looked at the hypothetical scenario where complete switch could happen, but of course that's not possible. And some of it means these devices, depending on the patient needs, would exist. But we are suggesting, means we are showing that by switching, these are the implications for the innards. Here again, we don't have much knowledge on their suitability as well and other features. So we have just assessed from the environmental perspective.
Okay, and I saw that you also included the waste aspect especially for the DPIs. Does that also include the whole time needed for decomposition of the plastics?
Yeah. So here we looked at the controlled disposal, which is either can be landfill or incineration. Again, it's not like disposal in another form. So yeah, for those both. So landfill, again, plastic generally doesn't biodegrade, but it stays in the as for more than 100 years or even more longer. So in those models, generally we would account what are the emissions which would occur from landfill, like in form either leachate and those, and then they will finally end in the environment. So these were all accounted for.
Okay, so from based on your studies, what would then be the optimum design option from an environmental point of view?
Okay, there are various options. So one of them could be to reduce the DPI's impact, or the even device-related impact would be to look for the reusable, for example, rather than a disposal type of device. But as we're saying that though some of the impacts are higher, but the magnitude is not that high for those devices, we can look at the low hanging fruit, which is at the moment is the emissions caused by propellants. And so probably looking at other alternatives, whether it's could be DPIs or other devices, or switching to propellant which has lower environmental impacts.
Okay, thank you very much. I can see there are many more questions, so keep them for later, or put them in an email to Sheila and Nikki, and we will forward them to Harish Jeswani. Thank you again for your interesting presentation.